Welcome back to the session on binomial distribution. In the last class, we discussed on binomial distribution. A discrete random variable capital X is said to follow a binomial distribution with parameters n and p if its PMF, that is probability mass function, is given by f of x equal to ncx p raised to x q raised to n minus x for x equal to 0, 1, 2, 3 up to n and equal to 0 otherwise, where p lying between 0 and 1 and p plus q equal to 1. We derived the expectation of x is equal to the product of parameters n and p, that is np, and the variance of x is npq. In this session, we shall discuss some realization of binomial distribution, then the recurrence relation connecting binomial distributions, then we shall discuss the moment generating function of binomial distribution, and we shall do some examples of binomial distribution. To realize the binomial distribution, consider a random experiment consisting of n independent trials. Each trial has two outcomes traditionally named as success and failure. The probability of getting a success in each trial is assumed to be same. Let it be p, that is p denotes the probability of success. Now, we want to find the probability of getting a particular number of success out of n independent trials. We define a random variable capital X as the number of successes out of n independent trials. Then X takes values 0, 1, 2, 3, etc. up to n. Since there are n independent trials, all trials may be success, no one may be success, or in between 0 and n may be success. Therefore, the number of successes x takes values 0, 1, 2, 3 up to n. Now, we want to find the probability of a particular number small x of successes out of this n independent trials. X number of successes means there are x times p, x times p, and n minus x times the failures, means n minus x times 1 minus p. Let 1 minus p be denoted as q, that is q into q into q etc. into q n minus x times q. But out of n independent trials, x number of successes may be occurred in ncx ways. Out of n independent trials, we can choose x number of successes in ncx ways. Therefore, by the product rule, the corresponding probability, that is probability of getting x number of successes out of this n independent trials is equal to n choose x p into p into p etc. into p, x times means p raised to x into q into etc. q up to n minus x times, that is q raised to n minus x, which is the probability mass function of a binomial distribution we just discussed in the last class. This is the realization of binomial distribution. Now, we have to prove a recurrence relation connecting the binomial distribution. By the definition of binomial distribution, we have f of x is equal to NCx, p raised to x, q raised to n minus x, for x equal to 0, 1, 2, 3 up to n and equal to 0 otherwise. Then f of x plus 1 is equal to, just to replace x with the x plus 1 in this definition, we get f of x plus 1 is equal to n choose x plus 1 p raised to x plus 1 into q raised to n minus of x plus 1. Now, we divide f of x plus 1 by f of x, we get f of x plus 1 divided by f of x is equal to n choose x plus 1, p raised to x plus 1 means p raised to x into p into q raised to n minus of x plus 1 divided by f of x is n choose x, p raised to x, q raised to n minus x. Here we can write n minus of x plus 1 as n minus x minus 1, that is q raised to n minus x into q raised to minus 1, which is equal to we know NCR is equal to n factorial divided by r factorial into n minus r factorial. We use this definition of NCR here. NCx plus 1 is equal to n factorial divided by here x plus 1 factorial into n minus of x plus 1, that is n minus x minus 1 factorial into here p raised to x and p raised to x cancelled, q raised to n minus x, q raised to n minus x cancelled, and the remaining terms are p in the numerator here p into q raised to minus 1 all divided by NCx is n factorial divided by x factorial into n minus x factorial. This is equal to p into q raised to minus 1 divided by here x plus 1 factorial. X plus 1 factorial can be written as x factorial into x plus 1, here n minus x minus 1 factorial into we multiply by the reciprocal of this denominator, we get x factorial into n minus x factorial divided by 1, that is x factorial into n minus x factorial can be written as n minus x minus 1 factorial into n minus x. Now, x factorial and x factorial cancelled. Here n minus x minus 1 factorial and n minus x minus 1 factorial in the denominator, both are cancelled, and the remaining terms are p into q raised to minus 1, that is p by q, into here n minus x divided by here x plus 1. That is in the left hand side, f of x plus 1 divided by f of x is equal to p by q into n minus x divided by x plus 1. This implies f of x plus 1 is equal to p by q into n minus x divided by x plus 1 into f of x. This is the recurrence relation. Of binomial distribution, that is a relation connecting f of x plus 1 and f of x. Now, we have to discuss the moment generating function of the binomial distribution. By the definition, the moment generating function is, notation is mxt, which is defined as expectation of e raised to tx, which is the definition of moment generating function. This is equal to, by the definition of expectation, we can write this as summation over all x e raised to tx into f of x, where f of x is the PMF of the discrete random variable capital is x. Here f of x is this, range of x is 0 to n. Therefore, this is equal to summation x varies from 0 to n e raised to tx into f of x is n choose x p raised to x q raised to n minus x, which is equal to summation over x from 0 to n. Here e raised to tx into p raised to x, we can write this as ncx into p e raised to t the whole raised to x, that is p raised to x into e raised to tx into q raised to n minus x. If we expand by substituting the possible values of x, we will get this as the binomial expansion of q plus p e raised to t all raised to n. That is the moment generating function of x is of binomial distribution is mxt is equal to q plus p e raised to t the whole raised to n. By using this moment generating function, we can find the moments, various moments of the distribution. We differentiate this moment generating function with respect to x, then we substitute t equal to 0, we will get the first moment, that is d by dx of d by dt with respect to x, we differentiate with respect to x, not with respect to t. we differentiate with respect to t, we get d by dt of mxt, that is we find the first derivative of this and we substitute t equal to 0, which will give the first moment, which is equal to by differentiation q plus p e raised to t all raised to n is n into q plus p e raised to t raised to n minus 1 into derivative of p e raised to t, that is p into e raised to t. At t equal to 0, we get mx dash 0. We denote the representation mx dash for d by dt of mx, and we put the substitution t equal to 0. We get when t equal to 0, this term is here n into q plus e raised to 0 is 1, that is q plus p raised to n minus 1 into p into e raised to 0 is 1, that is mx dash 0 is equal to n into q plus p all raised to n minus 1 into p, which is equal to n into here p plus q. P plus q is 1 in the definition. Therefore, this is equal to np, which is our expectation we just derived in the last class. That is the first moment is the expectation. Now, we differentiate this once again and we put t equal to 0, we will get e of x square. Now, d by d square by dt square of mxt is equal to, we differentiate this once again. Here np is a constant. Now, we use this is a function of t and e raised to t is another function of t. Therefore, we use the product rule of differentiation. Np into first function is this q plus p e raised to t raised to n minus 1 into derivative of e raised to t is e raised to t plus e raised to t into derivative of this term q plus p e raised to t all raised to n minus 1 is n minus 1 into q plus p e raised to t raised to n minus 2 into derivative of p e raised to t is p into e raised to t. At t equal to 0, we get mx double dash 0. We use the notation mx double dash for d square by dt square of mx and we put t equal to 0. We will get this as np into q plus p raised to n minus 1. Here e raised to t is 1, e raised to 0 is 1 and e raised to 0 is 1 plus here t when t equal to 0 e raised to 0 is 1. Therefore, n minus 1 into here q plus p raised to n minus 2 into p. Which is equal to np into p plus q is 1. Therefore, this is 1 raised to n minus 1, that is 1 plus here n minus 1 into this p plus q also equal to 1, 1 raised to n minus 2 is 1 into p, that is n minus 1 into p. This is equal to np into 1 plus np minus p. That is equal to np into here np 1 minus p is equal to from here 1 minus p is equal to q. Therefore, np into this np plus q, that is equal to np into np is n square p square plus npq. This is the second moment, that is it is denoted as expectation of x square. Now, by the definition of variance of x, we get variance of x is equal to expectation of x square minus expectation of x the whole square, that is equal to here n square p square. E of x square is this second moment about 0, that is n square p square plus n p q minus e of x the whole square. Expectation of x is n p, that is e of x whole square means n p whole square, that is n square p square, which is equal to n p q. That is variance of x is equal to n p q. We just derived this in the last class. We used the moment generating function mxt to derive the e of x equal to n p and the variance of x equal to n p q. Now, let us do some examples of binomial distribution. Consider this example, that is in 8 throws of a die, consider the success as getting the face 5 or 6. Then find the mean and standard deviation. Here probability of success small p is equal to probability of getting the face 5 or 6 in 8 throws of a die, which is equal to probability of getting 5 means 1 by 6 and probability of getting the face 6 is also 1 by 6. Therefore, 5 or means plus in the probability, that is equal to 2 times 1 by 6, that is 1 by 3. Therefore, q is equal to, that is probability of failure is equal to 1 minus p, that is 1 minus 1 by 3, that is equal to 2 by 3. Here the experiment is repeated 8 times. Therefore, we can take n is equal to 8. And corresponding variable, we define the variable capital X as the number of successes. Therefore, x takes values 0, 1, 2, 3, etc. up to 8, and x follows binomial distribution with parameters n and p, means f of x is equal to n c x p raised to x q raised to n minus x. Here n is 8 c x, p is 1 by 3 raised to x, q is here 2 by 3. 2 by 3 raised to 8 minus x, where x equal to 0, 1, 2, 3 up to 8. Also, for a binomial distribution, we know that expectation of x is equal to n into p. We have to find the expectation which is equal to n into p, means here n is 8 and p is 1 by 3, which is equal to 8 by 3, and variance of x is equal to n into p into q, which is equal to np is 8 by 3 into q is here 2 by 3, that is 16 by 9. Therefore, the standard deviation is defined as the positive square root of variance of x, which is equal to root of 16 by 9, that is equal to 4 by 3. Now, consider this problem. The probability of a man hitting a target is 1 by 4. How many times must he fire so that the probability of his hitting the target is greater than 2 by 3? We want to find the number of firings. Let n be the required number. Here we are given probability of success. Here we consider the success as hitting the target. Therefore, p is equal to 1 by 4, which is given. We want to find n. Also, one probability condition is given, that is the probability of his hitting the target is greater than 2 by 3, means p of x, where x is the number of successes, which should be greater than or equal to 1. In order to hit, there should be minimum one number. Therefore, p of x greater than or equal to 1 is greater than 2 by 3. We have to find n such that this probability equation is satisfied. Here f of x is equal to ncx p raised to x q raised to n minus x. Therefore, probability of x greater than or equal to 1 is f of 1 plus f of 2 plus etc. up to f of n, which can be taken as 1 minus p of x less than 1, which is greater than 2 by 3. That is 1 minus probability of x less than 1 means p of x equal to 0 is greater than 2 by 3. That is, we have to find n such that 1 minus f of 0 is greater than 2 by 3. That is, we have to find n such that 1 minus nc 0, p is here 1 by 4, 1 by 4 raised to 0. If p equal to 1 by 4, then q equal to 3 by 4. 3 by 4 raised to n minus 0 is greater than 2 by 3. That is 1 minus nc 0 is 1, 1 by 4 raised to 0 is 1, 3 by 4 raised to n is greater than 2 by 3, which implies 1 minus 2 by 3 is greater than 3 by 4 raised to n. We have to find n such that 1 minus 2 by 3 is greater than 3 by 4 raised to n. That is, we have to find n such that 1 minus 2 by 3 is 3 minus 2 by 3, that is 1 by 3 is greater than 3 by 4 raised to n. We have to find n such satisfying this inequality. One trial method, we can find the least value of n satisfying this inequality is 4. n is approximately equal to 4, that is the if we put n is equal to 1, this inequality does not satisfy. If we put n equal to 2, then this inequality is does not hold. If n equal to 3, inequality does not hold, but for n equal to 4, this inequality hold. Therefore, we take the number n approximately equal to 4. Therefore, the man has to fire 4 hits in order to satisfy this probability. Now, let me conclude this session. In this session, we discussed the realization of binomial distribution, moment generating function of binomial distribution, the recurrence relation connecting binomial distributions, and we worked out 2 examples of binomial distribution. Thank you for watching this session. Have a nice day.